All right, so the last couple of days we've been talking about identifying whether matter is a pure substance or a mixture. And when we talked about pure substances the other day, we said how it could be an elemental substance or a compound. And the example that we had in our notes was about taking sodium, which is a metal, chlorine, which is a gas, and how they can combine to make a new unique substance or a compound. So today we're talking about why do compounds form. So why do compounds form? Turns out atoms want to have a full valence electron level. So we talked about valence electrons way back in our first unit on atoms. Valence electrons, or the valence electron level, is the outermost orbit. So our valence electron level for lithium is the second orbit. For fluorine, it's also the second orbit. And for aluminum, it is the third orbital. Lithium has one valence electron because there's one in that outer orbit. Fluorine has 7 valence electrons, and aluminum has 3. Okay, so remember, valence electron level is the outermost orbit with electrons in it. Those electrons are the valence electrons. When we're looking at elements on the periodic table, how do we know how many valence electrons they have? Well, we could draw a Bohr diagram, just like we've done so here, or we can look at this handy little chart. We're going to ignore groups 3 through 12, which is the transition metals, and only talk about elements within groups 1 and 2, and then 13 through 18. Group 1 elements have 1 valence electron, and group 2 elements have 2. So lithium is in group 1. It has 1 valence electron. Then we have groups 13, which has 3, group 14 has 4, 15 has 5, 16 has 6, 17 has 7, group 18 has 8. So group 17, 7 valence electrons. The halogens, like fluorine, are in group 17, 1, 2, 3, 4, 5, 6, 7 valence electrons. Here's aluminum. It is in group 13, 1, 2, 3 valence electrons. Compounds are a way for atoms to share, ditch, or steal electrons in order to fill up their valence levels. So again, looking to answer the question, why do atoms form compounds? Well, in those previous examples, we had 3 atoms. None of them had a full valence electron level, which brings us to the octet rule. So why do atoms share, ditch, or steal electrons to fill up their valence levels? This is the reason why. Main group elements want their valence electron level to have 8 valence electrons. Octet means 8. All atoms are trying to fill their valence electron level with 8 valence electrons. That's why atoms share, steal, or ditch electrons. They're trying to accomplish this. So let's take a look at some examples here. Let's begin by drawing a Bohr diagram for the element oxygen. Oxygen, 8 protons, 8 neutrons, and then 8 electrons. Remember, the number of protons and electrons should be the same for a neutral atom. So we got 2 in the first orbit, 6 in the second orbit, and the second orbit here is its valence electron level, so it has 6 valence electrons. How many valence electrons does it have? It has 6. What would it have to do to get a full valence electron level? Well, it had to be one of two things. We could either add 2 more electrons, so gain 2 electrons, or we could try to get rid of all 6 of these. Well, in this case, for oxygen, what would be easier to do? Gain 2 electrons. So if we gained 2 more electrons, we would have 8 valence electrons, and that would follow the octet rule. Sodium. Bohr diagram for sodium, 11 protons, 12 neutrons. Also 11 protons, 2 in the first orbit, 8 in the second. And then in its valence level, it only has 1 valence electron. So how many valence electrons does it have? It has 1. What would it have to do to get a full valence? Well, we could add 7 more electrons to this orbit, or we could get rid of 1. In this circumstance, we're going to lose that 1 electron, because if we take this electron out, then what do we have? This becomes the valence level. And how many electrons are in that level already? There are 8, which is what all atoms want to have. So In the case of sodium, it would be easiest to get rid of one electron and then have a full valence level with 8 electrons in it. Draw a Bohr diagram for the element chlorine. Here we have 17 protons, 18 neutrons, and 17 electrons. 2 in the first orbit, 8 in the second orbit, and then in the valence level, there are 7 valence electrons. So, it has 7 valence electrons. What would we have to do to get a full valence level? Well, if we added one more electron, then we would have 8 in this layer, or just like in the previous example, we could get rid of 7 electrons, and then we'd have the second level as our new valence level, and it would have 8. Well, which one's going to be easiest? Well, gaining 1 electron would definitely be easier than trying to get rid of 7. So in the case of chlorine, it will gain 1 electron, and then it will have a full octet in that outer valence electron level. How about aluminum? Draw a Bohr diagram for aluminum. And that's what we get. 13 protons, 14 neutrons, 2 electrons in the first orbit, 8 in the next one, 3 in the third orbital. Should have known how to draw this one because you already had this Bohr diagram a couple slides ago. So we got 3 valence electrons. What would it have to do to get a full octet? Well, we could get rid of these 3, or we could add 5 to it. What's going to be easier? Losing 3 electrons. So if we lose 3 electrons again, we get rid of those 3. Now this orbit will become the valence level, and there are 8 electrons there. In our last example, draw a Bohr diagram for the element helium. For helium, we have 2 protons, 2 neutrons, and 2 valence electrons. So what would we have for number of valence electrons? Well, it would be 2. This first orbit is our outermost level, and it has 2 electrons in it. So what would we have to do to get a full valence level? Well, helium is a special case. Gain or lose 2, we would do neither this time. The first orbit only holds 2 electrons, so it's already full. Remember, helium is in group 18, so it is considered a noble gas. Noble gases already have 8 valence electrons, so they don't gain or lose electrons. Or in this one special circumstance, because helium is in period 1, its outermost electrons are in the first orbit, it only has 2. This is what makes noble gases such a special element family. They already follow the octet rule. They don't want to gain electrons. They don't want to lose electrons. They've got all the electrons they need. They don't want to share. They're not giving any away. They're not bringing any in. They are done. They are full. So they tend to not form compounds with other things. We only see them as highly unreactive gases. So in general, if you go back and take a look at the different examples, we had like aluminum and sodium as examples. Those are both metals. We had chlorine and oxygen as examples. Those are nonmetals. In general, metals will lose electrons to empty out their partly filled valence layer, since the layer underneath is already full of electrons. Versus nonmetals, like the oxygen and chlorine examples, nonmetals will gain electrons to complete their partially filled valence electron layers. And when that happens, when we share, gain, or ditch electrons, we can form different types of compounds. The 2 different kinds of compounds that we can get are called covalent compounds and ionic compounds. Covalent compounds are made of nonmetals. So we have multiple nonmetal atoms coming together, and they are created when atoms share their valence electrons. So nonmetals don't steal electrons from other atoms. They don't give their electrons away to other nonmetals. They instead just kind of share their electrons, and we're going to be talking about that next week. Versus ionic compounds, which are made of metals and nonmetals. When you have metals and nonmetals, metals like to give up their electrons. Non-metal